All right, simple harmonic motion, take two. So now we're going to try to figure out all of these quantities, but this time at some place other than either maximum stretch, maximum compression, those are by the way the same, or equilibrium. So in other words, some spot somewhere x prime, somewhere in between these two. So for most of these, it's just going to be a simple replacement of your x value with an x prime value. So the force, yeah, not quite as much as maximum, but we can calculate it by doing F times x prime. Acceleration, again, not quite as fast as when you released it here or when it compressed it at maximum here, but still follows the same equation. Potential energy at that spot, at somewhere in between here, 1/2 kx prime squared. Kinetic energy and velocity now are the things that are going to be a little bit more tricky to find out. I'm going to put kinetic energy as 1/2 mv prime squared because it's not the maximum velocity spot when it's flying through equilibrium, but some other velocity. And then how do we figure that out? Well, move this up a bit. We start with our potential energy at max. So that's when 100% of the stored energy in the spring is either here or here. So when 100% is potential, it will convert that potential into kinetic until it's at maximum kinetic right here. So some spot in between, it's both. It's both potential energy at x prime plus kinetic energy. And I'm going to put v prime for that one. So how do we figure that out? 1/2 kx squared goes here. 1/2 kx prime squared goes here for potential. And then you can actually solve for velocity prime when you know these two, maximum energy at stretch and x prime energy, somewhere in between. The 1/2 cancel. We're going to solve for v prime, and you end up with kx squared minus kx prime squared, all divided by m, and then take the square root to get some velocity, v prime, at an in-between spot, not maximum and not equilibrium. So that'll work for any spot in between. So let's move that up here into our table. So it'll be the square root of kx squared minus kx prime squared, all divided by m. Okay? So this is the table now with pretty much everything filled in. We're going to go on and do this, create this same table, but instead of simple harmonic motion of a mass on a spring, the next thing will be simple harmonic motion of a pendulum.